Great. So our next speaker will be Thomas Raml from the Max Planck Institute for Physics in Munich. And Thomas will be speaking about infinite distances, the scalar potential, and Ricci flow. Take it away, Thomas.
So thank you. So let me also start by thanking the organizers and actually everybody else for joining today. And I'm actually very happy that Amine gave this nice talk before me, talking about distances and scalar potential, because now I can actually somehow connect and give you a bit of an alternative but complementary perspective on the topic. So we'll be talking indeed about infinite distances, scalar potential. So this will be the first part. It's from a project that appeared on the arXiv last year in collaboration with Saskia Demulder and Lüst. And then in the second part, some work in progress that gives an alternative approach using a Ricci flow. So let me start by giving you the obligatory introductory Swampland slides. It will be very quick. So I think we're all somehow experts in this field. So by now, it's clear that quantum gravity, especially in the sense that the effective theories that can emerge as a low energy limit of a quantum gravity are somehow special, and not everything is possible. And the theories that can be coupled to quantum gravity are in the landscape, while the ones that cannot be put in the Swampland. And the Swampland program then is the aim to formulate some set of criteria to decide if there are theories in the landscape or in the Swampland. And there is by now a big net of different conjectures, while today I want to focus on the distance conjecture. But also it's somehow a little cousin, the Ricci Flow Conjecture, that I will discuss in the second part. So very quickly, the distance conjecture, well, familiar, is a statement about the breakdown of an effective field theory. In particular, if we go to large distances in our model space, we should encounter an infinite tower of states that becomes exponentially light. And the distance we use to measure is the one we get from the kinetic terms that we get after dimensional reduction. And the prime example for this is the circle compactification, so the trivial circle compactification from d to d minus 1 dimensions. If we do our compactification, we get an action like this. Here from the kinetic term, we can read off the metric on modular space, and after canonically normalizing, we see that there are two infinite distance points, 0 and infinity. And we also easily see the infinite towers of states that should arise, namely the KK modes for going to infinite radius and the string winding modes for going to RE0. But what is even nicer or very nice is that we have T-duality. So even if we had known only one of these two infinite distance limits and only one tower, we could have immediately known that there has to be a second infinite distance point, and we would have gotten the towers for free because T-duality exchanges the radius with one of the radius, so exchanges the two infinite distance points, and at the same time it changes winding and momentum modes. And here one sees that there's a very close connection between the distance conjecture and dualities, and that's why it's sometimes also called the duality conjecture. But then, of course, the question arises, while this is very simple, a picture for the circle, what happens if we want to look at a more complicated example? This is a much more challenging question, and to see especially also what T-duality can teach us in these settings. So if we want to go to, for example, curved spaces with maybe fluxes, generically, we will always generate the scalar potential from this curvature and fluxes. Furthermore, if we have the freedom to perform T-duality on these backgrounds, there might also be a change in topology. So T-duality can exchange topological invariants with a flux quanta, and therefore this picture of changing, for example, the circle, which is self-dual with each other, can change dramatically. And also in some settings, if we have enough T-duality to our disposal, we can end up with non-geometric backgrounds that I will discuss in a second. So I will discuss the non-geometric backgrounds that can arise by applying T-duality. And then we can ask, what can we learn from all of this for the Swampland Distance Conjecture? So roughly the approach I'm taking is I'm working with a purely bosonic setup, only an SNS sector of some d-dimensional effective theory. We have geometry in terms of external and internal space, and assuming some nice product structure, we can reduce. and we get the low energy EFT, where we now have the kinetic terms of our scalar fields and the scalar potential. And let me also say that I use the word moduli and scalar field and scalar field space equivalently. And then how does this metric in general look like? So one can compute this. So the first term is some multidimensional case of the width metric. And the second part here is the analog for also allowing the B field to depend on our scalar fields. And then the scalar potential basically comes from the internal part of our effective action. So basically just the internal geometry, the internal fluxes, and so on. And actually, the point I want to make is most easily discussed using an example, and I will use the 3-sphere with some flux on it. In particular, I use here, I plug in the metric for the sphere in the as a Hopf vibration, because this is particularly nice for doing T-duality, and I put k units of H flux on it. And very similar to the circle, I get the metric or modular space that has two infinite distance points, the radius 0 and infinity. But what is very different now, I also generate the scalar potential. But even more pressingly, I realize something that is different to the circle is that on a sphere, I cannot have any non-trivial winding. So as is easily measured by the fundamental group being 0, there are no loops that are not contractible, so there cannot be any non-trivial winding, which might already hint at some possible problem, because the winding modes were the ones that give you the light tower of states for going to RS0. So one can ask, how is this absence of winding modes compatible with T-duality? So I can apply T-duality. I want to know how are the states mapped that are needed for the distance conjecture, and what does this mean for the distance conjecture itself? So first, for T-duality, I will be quite brief here. So as I said, we have this 3-sphere with k units of H flux, and we T-dualize along the Hopf fiber. And the 3-sphere as a Hopf vibration is a well-defined circuit vibration. So this is a perfectly well-defined T-duality, and I will end up with, again, a non-trivial circle vibration over the 2-sphere, now with a circle that is of inverse radius. Then I notice with this, the total space with this E tilde. And now I have only one unit of H flux. And this is actually one form of the more general principle of topological T-duality, which here for well-defined circle vibrations exchanges the k units of H flux with here the first Chern number of this space E tilde, which gets now k, and the 1 unit of H flux, which corresponds to the first Chern of the 3-sphere being 1. And on the right-hand side, there are some exotic features, like, for example, you can have winding only up to zk. So you wind k minus 1 times, and after k times, you contract again. And I don't want to get into the details. In the paper, we worked out how indeed you can consistently match, for example, the absence of winding to the non-conservedness of momentum states on the dual. But what is more important is, while here on the right column, indeed, we see that we have light towers of states for going to RS infinity, given by our light momentum modes. For example, if you want to look at the sphere, there are simply no modes that become light in either picture of the dual pair I look at when I go to RS0, because the momentum modes become heavy, and there are simply no winding modes that can become light. But this is a bit problematic, because the 3-sphere, if I appropriately tune the flux, is a valid string background. It should be in the landscape. And I should indeed find the tower of states. It's a well-defined West-to-millimeter model at level k if you want, so there should not be any problem. However, there is nothing that can provide a tower for us. But now we can go back to the fact that there was a scalar potential in this case, given here by this expression in the right corner. Or here on the left, I plotted it. So at the point where r is equal to the square root of the level k, we sit in our conformal point. So this is the string vacua, and the potential looks like this. And the solution to this apparent problem we propose is the following. We say that in an effective field theory that can actually be lifted to a quantum theory of quantum gravity, so a theory that is in the landscape, a divergence in the scalar potential emerges when we approach an infinite distance point for which the target space geometry can simply not give rise to a Lighthouse states. So put differently, one can say that the divergence in the potential signals for us that this is actually a sick infinite distance point for a theory that is anyway well-defined, can be lifted to a well-defined quantum gravity. But one point that is important here, so implicitly for working, for making this statement, I somehow assumed that the distance conjecture is still valid also in the presence of this potential, especially in the presence of this divergence to potential. So while I can think of for approaching asymptotically flat direction, I would assume that this is fine. A priori, it's a strong statement to say that it also holds in the direction of this diverging potential. And actually, I want to come back to this point in a second when I discuss the work in progress. But before that, I want to highlight some other aspects that we discuss in the paper that is already out. So I showed you the metric on the moduli space, if you also take into account the variations of the B field. And one can divide this using an element from a double field theory where we don't need any details. It's generalized metric, and the only thing we need to know is that it's an element in OD, D. And the T-duality acts on it again by ODD transformation. And so by the invariance of the trace here, we see that we get immediately that this expression is invariant under T-duality, which is important or required even, because if we have two T-dual pairs, these should be completely equivalent. So we would like to have equivalent moduli spaces and equivalent moduli space metrics, which indeed we get, but only if we also allow for this variation of the flux in some sense. And another point, I want to come back now to the non-geometry. So the version of non-geometric spaces that I'm discussing is you can think of them as locally being Riemannian manifolds. However, the transition functions are allowed to be T-dualities. So if you think of a torus, if you go around your torus, you can glue your different patches with the most diffeomorphisms, while in a non-geometric background, you're also allowed to use T-duality. So in some sense, if you go around, you can jump in some sense from a small circle to a big circle. And since T-duality is a perfect symmetry of string theory, the string doesn't carry if we apply T-duality, so they are really, we cannot avoid them in string theory. And they are even nice in the sense of modular stabilization, because there will be new exotic fluxes, so-called Q and R fluxes, that appear now. And the basic question we wanted to ask is, do these backgrounds fit in the usual treatment in the Swampland, especially for the distance conjecture? Because usually these backgrounds are somehow ill-defined in the usual NSNS frame due to some monotonies that appear. And so the question is, how do we do even this previous reduction procedure? How do we obtain the metric and the potential, and how is this consistent for T-duality? Because these backgrounds can arise as T-duals of normal backgrounds. So again, I want them to have the same potentials, the same metric on moduli space. And there is a crucial point that has already been worked out some time ago, and this is you have to do some field redefinition from your initial metric, so H was the metric in the internal space, and B to some new object, again a metric, and this beta field, which is a bivector. And then one can rewrite the normal Lagrangian as a now so-called beta supergravity Lagrangian that is equivalent up to total derivative. And so this was worked out by these people here. And one can rewrite the action, and what one sees is that it's actually, after one goes to this new frame, everything is well-defined, and one gets indeed a consistent picture of getting the same potential and the same metric on modular space, but only after one has done this redefinition and moved to this beta frame. But in this sense, these at least easy non-geometric backgrounds that arise from T-duality fit into the, at least from this perspective, into the Swampland program and into the distance conjecture. And so this brings me now to the second part. So I want to come back to this question. In what sense is even this point RE0 still an infinite distance point? Or in what sense can we view it as infinite distance point when we have our potential? So this is somewhat different perspective on the same question or problem I posed before. And now I'm asking, in which sense is RE0 an infinite distance point in the presence of this potential? Is it in some sense reachable even if I have a divergent potential? And what is a good notion of distance? And okay, I mean, now we've had luckily already a talk about one approach to how you can incorporate also potentials into the distance conjecture. There is also another group that has published some work on this. But I also want to mention Davide De Biasio. He was a PhD student at the Max Planck Institute who looked at Ricci Flow and the Swampland program, and also Ricci Flow and potentials. And this is actually the direction I want to go. I want to take a somehow alternative approach and try to discuss this appearance of potentials using Ricci Flow and associated Ricci Flow conjecture as put forward by Keyas, Lüst, and Lüst. So what is Ricci Flow? Ricci Flow is an evolution equation, a partial differential equation for our metric that is sourced by the Ricci tensor, as put forward quite some time ago by Hamilton. And what is then the associated Ricci Flow conjecture? The Ricci Flow conjecture says take a family of metrics that satisfies this Ricci Flow equation. Then there is an infinite tower of states that becomes massless when approaching a fixed point, so 0 here on the right side, that is at infinite distance. And this is nice because it has an immediate consequence that is the ADS distance conjecture. So ADS is an Einstein space. I can write my Ricci tensor in this way. And all the time dependence goes into lambda. And I see that indeed, as t goes to infinity, I approach the flat space limit of lambda going to 0. And now I can look at the distance either by plugging in this solution into the usual form of the DeWitt metric, and I see that I get indeed an infinite distance, or as also proposed by these authors in the original publication, to define the distance in this case as the log of the Ricci scalar, so the curly r here is the Ricci scalar, in the initial point divided by the final point. And indeed, for this case, these two notions agree, and you get an infinite distance point, and you recover the ADS distance conjecture. But there is even more to it that has been done. So Perelman, in his seminal work of the Poincaré conjecture, he introduced what is now known as Perelman's combined flow. So this is basically the flow equation of the Ricci flow for the metric, with an additional flow equation for now a scalar field that in some sense, I will argue that we can think of it as the dilaton. And why is this particularly nice? Because this flow is gradient with respect to some functional that is called the entropy functional that is given by this curly f here, which we realize is basically the string effective action of just the metric and the dilaton, supplemented by some kind of unit volume constraint, generalized unit volume constraint that I will not really get into. And then one can realize that it's not only gradient, but this functional is monotonic along this flow. So it gives a natural candidate for definition of a distance. And one can formulate another version. This was also already done in the original publication of the Ricci flow conjecture. Now using this entropy functional and the combined flow. And one can say that the distance in field space along this combined flow is determined by this entropy functional. Every 0 lies at infinite distance and is accompanied by an infinite tower of massless states, where now the distance is to be taken as the log of the functional evaluated at the starting point divided by the final point. So if you set basically here the dilaton to 0, you will get the previous definition of having the Ricci scalars in the definition of the distance. This has been done, but we wanted to ask, can we do even more? So if we, for example, look at the NSNS sector, we should also somehow include the Kalb-Ramond field. And luckily, there is what is now known as generalized Ricci flow. And we want to see what are the possible implications of using this concept for the Swampland distance conjecture with the potential. So we take the NSNS sector, and we consider the generalized Ricci flow as introduced by this group here, where now we take the generating functional, so the entropy functional, to be the string effective action, Okay, supplemented again by this unit volume constraint. And then the gradient flow that I can get from this functional is now given by these equations here, and it will be exactly the beta functions of the low energy effective string action that define now the flow of our geometry, at least for the metric and the B field or H, the flux. And now I can say, well, I have a metric and a potential modular space, but derived in the end. So they both come from the background data I start in D dimensions. So I want to ask what are the implications of defining the distance in the presence of a potential that will be generated from this background by looking at the flow of these background quantities and defining a distance, either again now in analogy to what was done before as the log of these functionals, or without going into details, probably even better as this integral here on the right that reduces in special cases to the one on the left. And I will stay rather sketchy since it's work in progress, but I want to again discuss an example to highlight the basic idea. So taking again the sphere, now first without flux, the Ricci flow reduces to a flow of the radius. So this R here is the radius of the sphere. And this has a simple solution given by this expression here. And we see that it flows towards 0 radius at the time, at the finite time. So this is actually what the Ricci flow is doing in generality. It contracts regions with positive curvature and it expands regions with negative curvature. So this sphere flows from some initial radius to 0 radius. Or if I want to view it as the potential that arises if I compactify on the sphere, this is what the potential would look like. And I started in my initial point is 0, and I flow towards into the diverging scalar potential. And the distance, if I take it as the log of these two quantities, indeed we see it diverges in the limit of this R is 0 limit. And then I want to mention that here on this solution, one can see that in principle, I could even extend this flow back in time. So it's well defined if I put here a negative time. And then in the limit of going to minus infinity, I could even somehow approach back the infinite distance point of R is infinity, and I can calculate the distance, and this is again at infinite distance point. Although I want to stress that this is still something we're thinking about, what is actually the meaning of this natural direction of flow. And now what changes if I add the flux? Well, the defining flow equation gets more complicated. There is no analytic solution, but we see that for the radius is equal to the square root of the flux, level k. The flow stabilizes. So either starting from a bigger radius than that or a smaller, we will flow to the fixed point of having this radius at square root k. Or in terms of the potential that will arise that I already showed you before, this means if we start, for example, here, at some point at t is 0, we will flow towards the minimum of this potential, here where the beta functions vanish and I'm sitting on my string vacuum. Or I start from a smaller radius and I will also approach this point. And here we see now the new interpretation that here I cannot or I will not approach this infinite distance point. As from both directions, I will flow towards this fixed point that, as we see, will lie at a finite distance because the functional evaluated at this point is finite. So this gives a constant, a finite value of the distance. And also here, it's still, we need to think about what it means because in principle, one could also define here the flow backwards in time. And one could, in principle, also assign here an infinite distance in both directions to 0 and infinity, which would also be fine, since then we would have a notion of distance that would tell us indeed that we can think of it as an infinite distance point. So the idea was to look at the scalar potential using this Ricci flow it's nice because it's a monotonous function along the flow, this entropy functional, also in the generalized case. And so it defines a natural notion of distance. And it's quite intriguing that the flow equations are given by the beta functions of the string effective actions. So one can even think about it as an RG flow. But there are many open questions still that we are working on. That is, what is the natural role of the direction of this flow? Of course, one can look at flowing the whole d-dimensional background, for example, only flowing the n-dimensional compact part. And then one has to think about what does it mean to look at the 4D effective perspective? What is the role of the Einstein frame? And these are all things that we are looking at still. And furthermore, adding Raml fluxes to the flow and also non-geometric backgrounds, because all of this has a very nice formulation in terms of generalized geometry, which is very natural to look at T-duality and then also non-geometric flow equations. So, and let me very briefly now recap. So in the first part of the talk, I told you about the distance conjecture and the implications of T-duality if we look at curved spaces with fluxes. I told you about this invariance of the metric or modular space for abelian T-duality, the role of the scalar potential and the interplay with the absence of Itow states, as we argued, and the first step towards implement or looking at non-geometric backgrounds in connections with the distance conjecture. And there are actually many further directions and points we are already working on. For example, looking at more realistic setups to test our amendment to the distance conjecture, flux relations and the potential. Okay, I didn't really touch on this now, but then one can also look at generalized forms of T-duality and see how these fit into the distance or the Swampland program and what one can learn in both directions. Then, of course, the whole issue about the potential and the generalized fluxes and the different perspective to what was also done in other approaches. And then lastly, also a big question still is what about truly non-geometric spaces that don't arise as T-duals? What is the role? Probably not even so much in the Swampland, but there's valid string backgrounds in the landscape and what we can still learn there. And with this, I want to thank you all and I'm ready for questions.
Well, thank you, Thomas, for the very nice talk. Do we have any questions from the audience?
Thomas, please go ahead.
You can hear me? Yeah.
Yes.
Yeah, okay. I wanted to understand a bit why you said that if R goes to 0, there are no obvious light states. So imagine there's a D3 brane that's trapping the 3 sphere. Is the reason that you don't consider it as a potential light state because of the Fried-Witten effect? Or is it for another reason that you exclude this option?
The thing is that in principle, we can view the S3 with the flux completely by its own as an internal background. Maybe if we put it with Minkowski as a valid string background. So even without any addition, it should be a valid quantum, it should live to a valid quantum gravity, even without using, adding any branes or any additional degrees of freedom. So we were arguing that since there are really no candidates, without adding something, we need a different solution to.
But I'm not adding. I'm just saying string theory has D branes unavoidably. So if I add a wrapped D3 brane, why is it not a candidate light state?
Well, I mean, this would amount to also changing the effective action, right? I need to somehow add the D brane to my setup, but it was not there. It seems to me a bit unnatural to start from a given low energy effective theory, which in our case was just this NSNS sector, and then arguing that there should also appear the D3 branes.
Well, I think it's more related to the Fried-Witten effect, but we can discuss later.
Okay, yeah.
Thank you.
I add something?
Yeah, of course. Please, Dieter.
Thomas' question. I'm not sure, but isn't it so that you indeed there's a wrapped D3 brane which become light, but it provide only one light state, but never a tower of many light states in this limit. This is, I think, what is going to happen with the D3 brane. Maybe the Fried-Witten effect is also relevant, but it's like, yeah, it's not a tower of light states which is emerging there.
Unless I add, I mean, I have a higher wrapping number, right? I can just add charges.
I think something is wrong with the higher Epping numbers. I cannot give you the complete answer right now, but I think it's only one light state which arises there, like similar like to the conifold.
Okay. All right. Thank you.
Thank you, Dieter.
There is one question from the Harvard group.
Hi, thank you for the nice talk. I have a question about the T-duality. So you don't know if this T-duality is a T-duality symmetry or not?
Which one?
So when you plot this potential for the radius and it diverges to the left, the T-dualities that you're considering do you know if they are T-duality symmetries or just T-dualities? Because like if you're in type 2 string, T-duality will bring you from type 2A to type 2B, but if you're in heterotic, you actually have a symmetry. So you have a symmetry enhancement at a specific radius. So I cannot really make a distinction between what's going on for small radius and large radius. My question is if you're taking this into account.
I mean, for the T-duality, for the argument for the potential, the T-duality didn't really play such a big role. The T-duality in the first part was more for arguing how we can map the different states, the missing modes to the T-dual, which is this different circle vibration that
Right.
I mean, this is a purely NSNS bosonic sector that we are looking at.
Yeah, but I asked because I want to know if I should interpret that point where you have the minimum of the potential as a symmetry enhancement point. And if it is a symmetry enhancement point, then it's a finite distance singularity in the moduli space.
This point here, this is the string vacuum here, right? This is the conformer. If I look at it as a Western-Minometer model, this is where I am conformer.
Yeah. Yeah, but your Western-Minometer model could be heterotic or could be type 2. So if it is heterotic, then there's a symmetry enhancement there. And so what I mean by that is that there's no, you have one direction, which is large radius, which is infinite distance. And then you have one direction, which is finite distance singularity. So then if I have a divergence of the potential, I would say, well, it's just because I have a symmetry enhancement at this point.
But why does the signature, sorry, I'm not completely following, the signature
Yes.
enhancement at the minimum? What does it has to do with the divergent direction being at finite distance?
Yeah, well, I don't want to take much time, but just to give an example, which to me seems related. If you take the type 1 string and you put it on a circle and you do T-duality, then you can get a symmetry enhancement that comes from a divergence of the potential. You need these effects in the type 1 frame. So then I hit a point, I move in the moduli space, and I reach a point where I have a divergence of the potential and a divergence of, in this case, of dilaton profile. And at that point, I have a symmetry enhancement. I say, oh, I hit a finite distance singularity. And then if I want to keep going, I don't have a notion of keeping going. I just have to do T-duality and go back. So that's kind of the worry that I have. Like if you're doing something where you have a symmetry enhancement or not, is this heterotic with a model, or is it type 2? It's a bit confusing to me.
But what you just said seems not like a problem, but even maybe like a different interpretation of what I was saying, that that you should not access this direction where the potential diverges. Maybe what you just said is just a reformulation in terms of a different.
Okay, that's very good. Thank you. I will think about it more.
Thank you too. Very interesting.
Are there any other questions from the audience? Well, if not, let's thank Amine and Thomas again for their very nice talks. We'll meet again on October 15th. Stay tuned for the announcements of the talks then. And if you would like to give a talk, please sign up. Thanks. Bye-bye, everyone.
Bye, everyone. If you would like to still discuss with the speakers or ask something in a more informal manner, we will stop the recording now, but keep the meeting open for a few more minutes, so feel welcome to do so. Thank you very much for joining, and see you in 2 weeks.
Thank you.
Bye.
Bye.